In this video, I'm going to talk about what it means for a function to be continuous, and we're going to make a definition of continuity in terms of limits. First of all, we're going to start off with three things that destroy continuity. Okay? The first thing is this. Suppose I have a function that looks something like this. Okay? There's a hole in the graph at this value c. All right. Then this function, by our intuitive idea of what it means for a function to be continuous, would not be continuous. Another example of something that would not be continuous would be if I had a function that looked something like this, where there was actually a jump in the graph at this value c. Okay, so we can see by our intuitive idea of continuity, this function, because I have to jump from here up to here, would not be continuous. And a third example of something that is not continuous would be one that looks like this. Okay, so this function is defined everywhere, but the value of the function is not the same as what we would perceive to be the limit of the function. Okay, so these are three ways that continuity could be destroyed. The function here is not even defined at c, and that destroys continuity. Here the function is defined at c, but it's approaching a different value coming from the left side than it is coming from the right side. Okay, here the function is defined at c, but it's approaching the same value from the left as it does from the right. Okay, and therefore these three things destroy the continuity of a function. Okay, so with these three things in mind, we can actually give a definition of continuity. So a function f we'll call it f of x, is continuous at a point c if the following three things hold. Okay, so we have three things that destroy continuity, so we have to make a statement about each of these three things. So what destroyed the continuity here is the fact that the function is not defined at c. So the first rule we have to have is that the function f has to be defined at c, because if it's not defined at c, then we don't have continuity, as in example 1 here. However, that's not enough, because this function here and this function here are both defined at c, but they're still not continuous. So we have to have something else. In the second picture, even though the function is defined at c, the limit at c does not exist, right? Because if we tried to approach from this side, we would have a value down here, but if we tried to approach from this side, we have a different value up here. So the limit does not exist. So in order to fix this problem with continuity, we have to specify that the limit must exist at c. So the second thing that must be true is the limit that as x approaches c of f of x must exist. Okay? But that's still not enough, because if we look at example 3 here, here the limit exists, it's equal to whatever this value is here. The function is defined because we have this value here is f of c. So it satisfies condition 1, the function is defined at c. It satisfies condition 2, the limit exists at c. But what's wrong? The problem with this one is that the value of the function does not equal the limit of the function. So furthermore, in order to make a function continuous, we need not only to be defined at c and the limit to exist at c, but these two things must equal each other. So in other words, the limit as x approaches c of f of x needs to equal the value of the function. Okay? So if these three things are true, then we would have a function that is continuous. So we say that the function is continuous at the point c. So now we can say that the function is continuous on an open interval. We'll call that open interval AB. If it's continuous at every point in the open interval AB. Okay, so that would be the definition of a continuous function. Now, a function can have a discontinuity, and there are actually two types of discontinuity. In examples 1 and 3 here, these discontinuities are what we call removable. So that's a removable discontinuity, and so is this one. Okay, and the reason that we call these removable is that we can actually redefine the function at c in order to make the function continuous. So in other words, if I redefine this value here to be f of c, I've made a continuous function, so I have removed the discontinuity. If I redefine this function and make this value f of c, then I have removed the discontinuity. So we say that a discontinuity is removable if it can be made continuous by redefining the function. Okay? So a removable discontinuity, if we can redefine the function and make it continuous. Now, in the case of this second one here, this is a non-removable discontinuity. Okay, because if we tried to redefine the function, remember that for it to be continuous, however we define the function has to equal the limit of the function. But we can't do that because the limit of this function at c does not exist. So there's no way to redefine this function so that we would remove the discontinuity. So that one is considered a non-removable discontinuity. All right, so as an example, let us discuss the continuity of this function. F of x equals x squared plus 2x over x squared minus 4. All right, so first of all, we have a rational function. Remember, our three conditions of continuity is the function has to be defined, the limit has to exist, and the two values need to be equal. So this function, being a rational function, is not defined because at certain values, because if we factor the denominator here, okay, we can see that this function is not defined at x equals -2 and at x equals 2. Okay? Therefore, this function cannot be continuous at these two values. However, the function is continuous everywhere else because it's a rational function. And remember that we said for a rational function, if we look at the limit as x approaches c of, we'll call it p of x over q of x, this is just equal to p of c over q of c, as long as q of c is not equal to 0. Okay? So we've already eliminated the 2 points where q of c is equal to 0. So that means for any other c, this is going to be true. And therefore, we have that the limit exists, the function is defined, and the limit equals the value of the function. We satisfy the three conditions for continuity. Function is defined, the limit exists, and the two are equal. All right, so that means that these values are the only two places where this function is discontinuous. Now we have to determine what type of discontinuities they are. Are they removable or are they non-removable? If we go back up here, we see that pretty much if the limit exists, we can redefine the function so that the limit equals the value of the function, and therefore we have a removable discontinuity. But if the limit does not exist, as was in this case here in the middle, then we have a non-removable discontinuity because there's no way to redefine the function. So to determine whether these discontinuities are removable or non-removable, we simply have to look at the limit. Now, before I look at the limit, I'm going to actually simplify this function by factoring. The numerator is x times x plus 2, and the denominator is x plus 2 times x minus 2. All right, so if we want to determine whether I have a removable or a non-removable discontinuity of these two values, I'm going to look at the limit as x approaches, as x approaches these two values. So I'm going to look at the limit as x approaches -2 of my function, and I'm going to look at the limit as x approaches 2 of my function. Now, the bottom line is, if this limit exists, then I can redefine the function, and it will be a removable discontinuity. And if the limit does not exist, then I cannot redefine the function, and it'll be a non-removable discontinuity. All right, so in this case, in both cases, these limits will be equal to the limit of x over x minus 2, as long as x is not equal to -2, the two functions agree, right? All right, so in both cases, we have that this limit will equal the limit as x approaches -2 of x over x minus 2, and that limit is equal to, it's a rational function, denominator is not equal to 0, so I can simply plug in, and I get -2 over -2 minus 2, which is equal to 1/2. -2 over -4 is positive 1/2. All right. If I look at this one, then this limit is equal to the limit as x approaches 2. And again, we can use the reduced function. And now if I plug in a 2, I actually get 2 over 0, which we said is undefined and therefore does not exist. So our final analysis is that this function has a removable discontinuity at x equals -2, because the limit does exist, so I can redefine the function to equal 1/2 at that point. And we have a non-removable discontinuity at x equals +2, because the limit does not exist. Therefore, I cannot redefine the function. And the function is continuous everywhere else.